Hei! Tekna bygg og anlegg, Tekna Klima og Tekna biomangfold har i dag invitert til en digitalt lunsjmøte, der du får høre internasjonale erfaringer med mineraler og biogene byggematerialer. Medlemmer av NITO og nettverket FutureBuild er også invitert. Max Wittrup Jensen, daglig leder i LavKarbonBygg AS, er initiativtaker, så vi må takke han for dette lunsjwebinaret. Er mer bruk av ultra-lavkarbonmaterialer i norsk byggebransje å tro på julenissen? Eller er det relevant byggematerialer sett opp mot Parisavtalen? Dere kan stille spørsmål underveis via Slido i denne rett under her, som vil bli besvart i etterkant av seminaret og gjort tilgjengelig med presentasjonene. Vi får nok ikke tid til å svare på alt av spørsmål underveis, men gjerne still spørsmål underveis. Jeg heter Cathrine Strande Straube og jobber som rådgiver i Tekna med Klima og Bærekraft, og skal lose dere gjennom dette lunsjwebinaret. Først ut er doktor i økologi, kommunikasjonsansvarlig i BIOFOKUS, Ulrika Jansson. Ulrika legger ut med oppdagelser omkring langtidseffekten av materialutvinning til det vi nå ser på som LavKarbonBygg. Effekter som ikke er inkludert i industriens livssyklusregnskap og EPD-er. Ulrika, er du med oss?
Jeg er med.
Ja, vær så god til deg.
Tusen takk. Først vil jeg takke for invitasjonen, og få være med i denne gjengen føles som en ære. Og jeg vil gjerne bidra med å belyse hva som skjer i skogen ved uttak av tømmer, og hvilken tidshorisont vi bør sammenligne langtidslagring i bygg med. Og først så ønsker jeg å tegne det store bildet. Hva tåler planeten vår av miljøutfordringer? Sen vil jeg snakke litt om hvilke forpliktelser vi har i internasjonale og nasjonale avtaler og vedtak. Så vil jeg komme inn på hvor i skogen dette her karbonet som vi snakker så mye om dagen faktisk finnes, og hva som skjer med karbonet i skogen ved hogst. Og så vil jeg avslutte med en liten slide om langtidslagring av karbon i skog kontra langtidslagring av karbon i byggematerialer. Skal vi se om jeg får opp. Så, hvilke miljøproblem er egentlig størst? Stockholm Resilience Center har laget en god visuell oversikt over dette her, og de peker på at det største trusselen er forlust av naturmangfold. Og det ser ni som den store oransje figuren lengst til venstre, nede til venstre. Sen er det et stort trussel at nitrogenets kretsløp er forstyrret, og på tredje plass kommer det som vi da skal inn på først og fremst i dag, klimaendringene. Når det gjelder forpliktelser som Norge har, så har vi på skog- og skogarealsiden, så har vi forpliktet oss at innen 2020 så skal vi ha minst 17% av landarealet og ferskvannsarealet bevart effektivt i godt sammenhengende systemer. Og disse økosystemene skal være robuste. Det biologiske mangfoldets bidrag som karbonlager skal være forsterket gjennom bevaring og restaurering. Som dere kanskje kjenner til, så er dette her mål som vi ikke klarte å nå for 2020. Rent konkret i Norge på skog så har vi et vedtatt mål for skogvern på 10%, mens det oppnådde skogvernet ligger på 5%. Og av det så er det da bare 1%, litt mindre enn 1% faktisk, som er skog av høy og svært høy bonitet, det vil si skog som vokser raskt. Når det gjelder klima så er våre forpliktelser internasjonalt at vi skal ikke få en temperaturøkning på kloden på mer enn 2 grader før 2100, og helst ikke mer enn 0,5 grad. Og for 2100 så skal vi være klimaneutrale. Denne illustrasjonen har jeg lånt fra FN-sambandet. Så til skogen og karbonet. I en boreal skog, som det vi har i Norge, altså den skogen på den nordre halvkule, så faktisk 70% av karbonet lagret i bakken, og bare 30% finnes i trær og annen vegetasjon, inkludert og i tømmer. Og man vet også at karbonet i skogjorden hardere bundet i en gammel skogjord enn i en ung skogsjord. Og det handler om hvilken type sopp som finnes i i den unge skogen og den gamle skogen. Så vet man også at karbon fortsetter å lagres i gammel skog, også etter at den har blitt gammel. Og hva skjer da når vi hogger skogen? Da har jeg delt det her opp på hva som skjer over bakken og hva som skjer under bakken. Og under bakken så skjer det en stor nedbrytning av røtter og små materiale, organisk materiale. Og den nedbrytningen øker. Og i løpet av få år så har vi brytet ned mye av karbonet i bakken. Og mange sopp såkalte sopprotsopp, som danner mykorrhiza med trær. Og denne typen sopp veldig viktig for karbonlagringen i jorda. Når vi hogger skogen, så hogger vi trærne som gir disse soppene maten sin, sukkeret fra fotosyntesen. Og da dør de, og de brytes ned. Så i bakken så får vi utslipp av karbon etter hogst. Over bakken så ser vi da at vi tar ut tømmer, og ca. 50% av den skogen vi hogger i Norge går i dag til sagbruk, mens den andre halvparten går direkte til mer kortlevde produkter. Men av de trærne som da går til sagbruk og skal bli til byggematerialer, så forsvinner omtrent halvparten. Mye fordi at den stokker rund. Du får ikke så mye plankematerialer ut av en stokk. Så samlet blir da 25% av biomassen som tas ut av skogen blir da såkalt langlagret bygningsmateriale eller langlagret karbon i bygningsmateriale. Mens 75% blir til energi eller kortlevde produkter som gir da utslipp etter hogst. Ganske kort tid etter hogst. Og så vil jeg bruke litt tid på å forklare denne figuren her. Den lånt fra en rapport som heter Vern eller bruk av skog som klimatiltak, som laget av Landbruksdirektoratet, Miljødirektoratet og NIBIO. Og den sier at det tar omtrent en omløpsperiode, det vil si 60-120 år, før den karbonet som forsvinner ut av skogen ved hogst, igjen lagret inn. Altså at innlagring og utslipp har gått i null. Og det har jeg da tegnet inn som den første. Om ni ser den blå linjen, så står det 2020 til venstre og 2100 et stykke inn. Det altså da vi skal være i null på utslipp. Men da hogger vi skogen igjen. Så har vi en omlagsperiode på 60-120 år til. Jeg tok et middeltall på 80 år, sånn cirka. Og så ser vi hva som skjer. Så ved gjentatt hogst så minker karbonlagret i skog. Om vi klarer å unngå fossile utslipp i like stor grad eller i større grad enn det vi har fått sluppet ut og tatt opp, så får vi en balanse der vi kanskje klarer å unngå de store utslippene. Men hvordan vi sikre på at vi faktisk unngår fossile utslipp og ikke både slipper ut fra skogen og fortsetter å øke utslippene fra hogst? Så sa jeg da at 25% av hogsten blir såkalt langlagret karbon, og hva betyr det i et bygg? Ja, i sånne her gamle bygg som jeg har illustrert med på bildet, så kan de lagres i flere hundre år. Ta eksempel stavkirker. Men det vanlige jo at de lagres i bygg mellom 20 til 80 år. Og det høres jo ganske mye ut. Men om man da tenker på hvor lenge karbonet lagres i en intakt skog, så vet vi at en skog kan bli over 300 år gammel, og det finnes eksempler på 400, 500 og 600 år gamle grantrær også. Mens en furu kan bli 600 år gammel, og gjerne enda eldre om den får stå i ro. De stående døde träden etter at treet har levd i sine 600 år, så kan det stå da i kanskje 100 år til som et dødt tre. Og så kan det falle ned og bli liggende død ved, og stå i 50 år til etter det. Eller ligger da i 50 år til etter det. Så langlagring i skog kan altså da være over 300 år, pluss. Til sammenligning da med de 20-80 årene som karbonet langlagres i et bygg. Så vil jeg avslutte med å si at vi skal ha et aktivt skogbruk i Norge av flere grunner, men kanskje ikke klima den største grunnen. Vi har mindre enn en tregenerasjon på oss å redusere utslippene. Så vi kan ikke tenke at gjentatt hogst over tid til slutt vil gi et eventuelt redusert utslipp. Vi må redusere utslippene nå. Og med det tidsperspektivet til grunn vil ofte vern være da et bedre klimatiltak enn hogst i skogbruket. Og at for at karbonlagring i bygg da skal være reelt klimavennlig, må vi sikre at karbonet lagres lengre tid i et bygg enn i naturen. Takk for meg.
Tusen takk, Ulrika. Veldig interessant og bra start. Da hopper vi fra Sverige, hvis det var der du satt, til Toronto i Canada for å høre fra neste gjest, Chris Magwood. I 1998 startet Chris Camelback Construction, et designbyggfirma fokusert på halmballkonstruksjon og fornybar energi. Men har siden 2011 vært daglig leder og lærer ved The Endeavour Center. På grunn av tidsforskjell Chris med via en forhåndsinnspilt presentasjon, men det bare å stille spørsmål, #ultra, rett under her, og de vil bli besvart senere. Da sier vi snurr film til Chris Magwood.
In a session called Carbon Drawdown Now, Turning Buildings into Carbon Sinks. I'm going to attempt to go pretty quickly through a lot of material here. So I hope you can stick with me. It's fairly information dense, but hopefully it will be rewarding in the end. What I want to do is start with a look at how we right now look at the carbon footprint of buildings through life cycle assessment, looking at the full life cycle impact using the end of life of a building as our sort of marker. And so I'm going to build you a grid where carbon storage is below the line. That's carbon that's been taken out of the atmosphere, and carbon emissions is above the line. So that's what we're emitting right now, contributing to climate change. And we'll include the A phase of life cycle assessment, which is the product and construction phase, the use phase, the B section, and end of life, the C section. And what you tend to see when you look at a typical life cycle assessment is you get a value, in this case where that red dot is, at the end of life, typically looking at a 60 to 100 year lifespan for the building, and you add up all the emissions that occur over the course of that lifetime and express it as a number at the end of life. And so often when we look at bio-based materials, the number that we get over there at the right for end of life isn't that different than the one that we get for non-biogenic building materials. And when we look at it this way, it's like, oh, biogenic building materials, not that big a difference. And we don't really see the full picture because we're looking at this very sort of static version of life cycle assessment. So you get a similar result between the materials, but it doesn't really tell you the whole story. So what I'd like to do is sort of paint you a more dynamic comparison here, where we trace the timing and the pathway of those emissions and understand more completely how certain materials contribute to climate change and others can actually reverse it. So when we talk about typical building materials, the full A cycle of the life cycle phase adds emissions to the atmosphere. And obviously the scale of those can change dramatically, but everything that happens along the way to turning that material into a building product adds emissions. And so you reach a point when the building is built where over the use phase, with the exception of some blips for maintenance and replacement, that line stays pretty static. And then at end of life, we're usually given two options, landfill or recycling, and therefore there's that dot that we ended up with in the static comparison. But you can see that it's not just a dot in time way over here, that there's sort of a burst of emissions at the initial stage of that project that all relate to the emissions from the materials. When we look at bio-based materials, there is usually a small burst of emissions from the activities that accompany planting whatever the bio-based material is. But then there's a long period of photosynthetic drawdown where those plants are pulling CO2 out of the atmosphere and using the carbon atoms to basically build their own structure and releasing the oxygen atoms back out to the atmosphere. Then, similar to all materials, there is a range of emissions that happen from harvesting through to construction that put some emissions back into the atmosphere. But for all of the bio-based materials that I've looked at in my studies, that amount is always less than the amount that has been drawn out of the atmosphere in generating the plant in the first place. And therefore, over the lifespan of the building, there's actually a net carbon reduction in the atmosphere because we're holding on to carbon that would have otherwise gone back to the atmosphere. That's now in our building. It's not going back. And so we have that line showing us that over the lifespan of our building, however long that happens to be, we're storing carbon. And then at end of life, we can paint a whole bunch of scenarios, some of which are really great, like reusing or recycling that carbon and keeping it out of the atmosphere, turning it into biochar and keeping a bunch of it out of the atmosphere, using it for combined heat and power and calling it sort of carbon neutral, or in the worst case, landfilling it and it turning into methane. And that's often how we get to that static dot that we saw in the first place in the static version of LCA. But even this graph is sort of misleading because it makes us think that there's a single number. With the red one, we get to that line and there's a number, and the bottom one, we get to a line and there's a number. But the actual climate impact of these materials is the area under the line. So once those emissions go into the atmosphere, they stay in the atmosphere for a very long time, and they continue to trap heat and they continue to drive radiative forcing year after year after year after we emit them. And so the impact on the climate isn't just a number out here at the end of life, it's the cumulative impact of the area under that red line. Whereas when we have a carbon storing material, the cumulative impact, again, is the impact of having less carbon in the atmosphere over that whole period of time. So it's a very different picture when you think about the areas above and below those lines than if you just think about the red or the green dot over at the far right. Now, obviously, when we return bio-based materials, when we get rid of them, if they do create methane or if the carbon is released to the atmosphere, there is emissions again at the end. But again, if you look at the total area under the line, it's still been a significant carbon drawdown, even at the end of its lifespan. Now, end of lifespan of the building isn't end of lifespan of the effects of the emissions. So here we're pulling out of it and realizing, once we put those emissions into the atmosphere, they keep going. And so they degrade, over time. And so eventually their impact will taper off. But if we're looking at a 100-year life cycle assessment, the emissions don't poof out of the atmosphere at 100 years. They stay there, and depending on what they are, they degrade. But the impact that we incur way up here at the front end of the project has ramifications that last more than the century that we tend to look at. And similarly, that burst of emissions at the end of a life of the biogenic building material is really just a sort of nullification or a cancellation of the carbon that was drawn out of the atmosphere in the first place. So most of that isn't new emissions. The only part that's new emissions is the little bit that was emitted in making the material in the first place. And so that, carries on if the material goes back to the atmosphere. but it's a much smaller amount than all the carbon that was in the materials in the first place. So that sort of paints this picture where we start to understand, making buildings with bio-based building materials, if they have a net carbon storage, makes a lot of sense. It's in fact one of the only things we can do in the building world to actually reverse climate change rather than just lower our impacts. So bringing that red line down is great. We absolutely need to do that. Every material that has emissions, we need to get those down. But if we can at the same time be using a bunch of materials that offer this carbon storage, then we accomplish something better than just less bad. We actually accomplish something more good. And this isn't just my theory. There is an entire field of climate science that looks at the value of biomass as meaningful storage, and typically at around the sort of 45 to 50-year window, that's when we see that the ton of carbon stored at the beginning of a project has reached its full value. It's offset a ton of carbon at the start of the project. So this means that buildings which typically last more than 40 or 50 years will see the full value of that carbon storage regardless of what happens to those materials at the end of their life. Now, we tend to think about this biomass in buildings as timber, as trees. The thing that we have to remember with timber, and I think there are other sessions on this today, so I'm not going to get into this in great depth, is that because forests are such important carbon sinks on the planet, if by doing timber buildings, we make the carbon pool smaller in forests while making the carbon pool of forest products bigger, we're not actually doing anything net better for the environment. If we're just moving carbon from here to here, and in fact reducing the ability of forests to continue to absorb carbon, just that transfer does us no good. So we have to really make sure that to do timber and carbon storage in buildings properly, the forest carbon stock has to get bigger as we remove timber from it, or else there's no net good. What I'm more excited about, and what I think is the point of today's presentations, is to look at other forms of biomass, in particular agricultural residues and waste streams. Now, these are all materials that have they're plant-based. They've pulled that CO2 out of the atmosphere. They've used it to build their plant bodies. And in typical fashion, if we don't interrupt this process, all of that CO2 ends up back in the atmosphere fairly quickly. It burns off, it rots off, whatever, if it's of no use to us, we tend to just let that carbon go back to the atmosphere. So you have this huge amount of carbon that's drawn down, but it typically just cycles right back up into the atmosphere. So what we're talking about, or what I'm proposing today, is basically just interrupting that cycle for the lifespan of a building, or ideally the lifespan of a building, or 2 or 3 would be even better. But here we're going to draw that CO2 out of the atmosphere. We're going to take a bunch of that residue material and put it into a building for 60 years, 70 years, 100 years, 200 years, however long we can, and it won't go back to the atmosphere over that period of time. And if we can get the rest of our act together on the planet and bring our actual fossil fuel emissions down close to zero, then this is a meaningful thing that we can do now to get us on a climate smart path. There is billions of tons of biomass available on the planet that cycles around this way. Here's a couple of studies done in the US showing that there's between sort of 670 million to 1.6 billion tons of annual biomass residue available just in that country. But it happens all over the world. A case in point, grain straw. We grow about 2.16 billion tons of this annually, and the amount of carbon that straw has drawn out of the atmosphere is 4 billion tons, which is India's contribution to global warming, is all drawn out of the atmosphere by grain straw every year, but we tend to just let it go right back into the atmosphere again. And so what we're suggesting is you interrupt that pattern, you make buildings like this building using, straw bale panels or straw sips or blown straw insulation or compressed straw panels or straw blocks, or, there are so many products that can be made out of just this one type of agricultural residue that's capable of eliminating India's emissions completely by putting it into our buildings. And I'll just wrap up by showing you this at work in a project that we did here at Trent University, where they needed a new forensic science classroom. And we used our new tool called BEAM, which is a material emissions estimator that includes all these biomass materials and their storage, all calculated according to a consistent methodology. And here we were able to help the university take a building that in its original form was going to have about 211 tons of emissions associated with making the materials for that building. And we work with them to look for suitable biomaterial replacements wherever possible. And we were able to get that building in its as-built form down to pretty much a carbon neutral building. It says here, minus 6 tons of carbon stored. So there's a little bit of net storage, but the important thing is that we've gone from over 200 tons of emissions down to a little bit of storage. So that whole 215 tons, that's the difference between these two, that's the difference to the atmosphere just in this single building. And so if we can multiply that across our entire building stock globally, then we will have made a massive, massive difference in addressing climate change. So thanks for listening, and I look forward to the question and answer period.
Tusen takk, Chris Magwood, i en forhåndsinnspilt film. Det var jo nesten som å føle at vi var der. Minner om at vi kan stille spørsmål til #ultra fortsatt. Ser at det har kommet inn noen spørsmål. Kjempebra, de vil bli besvart avslutningsvis med presentasjonene. Minner om det. Inspirasjon til dagens webinar kommer egentlig fra den imponerende 45 minutters presentasjonen Martin Haas ga i februar i et seminar arrangert av Norsk Arkitekters Landsforbund. Arkitekt Martin Haas har lenge spesialisert seg i innovativ og bærekraftig arkitektur. Siden 2012 som partner i arkitektfirma Haas Cooks Hermisch, tror det var cirka riktig sagt, Studio 2050. Martin er visepresident i DGNB, German Sustainable Building Council. Martin Haas, er du med oss i dag?
So, thank you very much for your introduction. I didn't understand much of it. Sorry for that. Sorry for not speaking your language. So, shall I start with my presentation? Is that okay?
That's perfect.
Okay, so thank you very much. We are an office here in Stuttgart, roughly 30 person, and as you mentioned, I understand it a bit. We are very interested in the term of sustainability and how to generate better buildings, and so the first approach is to build as simple as possible, to work as much with what we have already, so microclimatic issues, and to work with the climate, not against the climate, to reduce all technical elements upfront by design, by orientation, by working with daylight, working with ventilation. We in Germany have the advantage that 80% of our time we would not need any heating or cooling. So summarizing, as simple as possible. If technical elements are needed, then it's an add-on. It's never part of the structure. It should be removable. It should be easy to build. And that is our strategy. And that was also part of the design when we started to develop a concept for Alnatura, which is a biotech organic food company here in Germany. Not biotech, sorry, organic food. The new headquarters. We started with the simple approach of using from the site whatever we can use. So it's in a location close of Darmstadt, a mid-sized town here in Europe, in Germany. And it's a bit remote. We are close to the inner city center. It was a former military camp. And you see the sealed areas, that was parking devices for tanks, and the staff buildings you can see on the right side. It's close to a forest. Forest on the west side means that we have from the wind direction an optimum natural wind device, so we have natural ventilation possibilities. And when we generated the layout of the house, we didn't start architecturally with a design, with a drawing. We started in labeling, giving ourselves criteria under which Alnatura should be developed. And that was to be as much as possible climatic neutral, to work with materials which are renewable, an optimal kind of life cycle analysis, and the renewable building materials we should find as in close proximity as possible. We did a typical survey of solar gains, of embedded energy in for the geothermal devices, of shared facilities. Do we have usages where we generate warmth and can reuse it for other areas? And moisture in the area. And when we layouted the house, we did it under microclimatic considerations. So a perfect north-south orientation helped to generate daylight qualities in the inside, but not having overheating issues. We raised the heights of the ceilings to have deeper areas where daylight hit the surfaces inside, to have an optimized daylight enlighted kind of facility. We shrink the volume to have a very good ratio between insulated areas and outside facilities. Then with the northeast, east-west direction, we also had an earth duct underneath the building, so we suck in the fresh air from the forest in the west, and we guide it in the earth duct into the building, and with this chimney effect, we can generate a natural ventilation device, and we use the forest as a natural cooling device. In the summer, in the forest area, you have roughly 5 to 6 degree cooler air in the summer by evaporation cooling. So that was the layout. And when we came to how we build it, it was our wish to make it as simple as possible. In a typical office layout, on the left side, you see that you have so many layers, raised ceilings, raised floors, you have construction areas, you have insulation areas, you have cladding areas. So summarizing, you spend 1/3 of a building volume just for untrapped volume areas, so technical elements. And the nice layout of a simplified building is that the room is what you see, and there is no hidden area whatsoever. And the simplicity could also help to reduce building costs, to reduce mechanical issues, to maintenance issues and all that. So that was the guidance, that was the wish. And we started, and we had a partner in the TU München, where we did some analysis for embedded energy, how to build as simple as possible, and to check from materials, production stage, construction stage, usage, and end-of-life scenarios. We did a kind of like an MRT. So we cut our building envelope in pieces and checked the embedded energy with various materials. And we ended with rammed earth. When we started that, I didn't have a clue about rammed earth. We were happy to join Martin Rau, who is speak after me, so that fits perfectly. And we had a couple of months time to develop a mock-up of a facade which could embed not only rammed earth, but also heating and cooling, because in our simulation we figured out that with this kind of bigger volume to reduce, to have optimized daylight qualities, we will have a heating issue in the winter. So the building will perform quite positively in the summer, but will cool down too much in the winter. So we had to introduce an heating system. And since we didn't have any layers, no raised ceilings, a very limited kind of a double floor, the wall was a perfect position to embed a radiant heating device linked with a geothermal facilities and the heat pump. And that took us a while, and together with Martin we worked quite long, and together with Transolar and with our structural engineer, to develop a concept of a rammed earth element prefabricated. For insulation we used here Cravel glass, foam glass. The machinery, you see, most likely Martin will tell a bit more about the way we did it on site. You can see here the wires coming out. That is the embedded heating and cooling device we put in the inner part of this massive rammed earth block. So you can see here the way it is constructed. So it's not a monolithic element. It's engineered with two sides. So we have an outside element, roughly 35 centimeter, rammed earth with lime barriers against erosion. Then we have the insulation with a Cravel, with a foam glass Cravel, and we have an inside rammed earth block where we have the heating and cooling device, so the radiant heating also rammed in. So you see here the production facility running through a bit of limited of time. Just to give you an overview about the project, we produced it on site. That was very good to link the client with this new material. It's an old material, but it is reintroduced into modern architecture, into modern office architecture. So it was a bit of an invention. And we had to deal with the typical cliché concerns about erosion, etc. But together with Martin's knowledge and experience, we managed easily then to convince a client who was very fond of having a natural material for his facade. So you see it under production. The elements themselves were roughly a meter high, 3.5 meters in length. You see here the cut where the window, the facade connection comes in, and you see that the lime erosion barriers at the corners are increased, are enhanced. We had a roof out of wood construction. It was the first time that this kind of a height rammed earth facade was introduced in Europe, with this kind of embedded heating device. The facility, after it was finished, works brilliantly. So we have it now on site for 3 years already, or 2.5 years. So we had 2 harsh summers and 2 harsh winters, and in both periods of years, the facade works very nicely, and the client is still happy. Big room. So in the inside, it doesn't feel like being in a rammed earth sealed kind of a building. We also do monitoring. You see here in the monitors easily how good the rammed earth works with moisture in the building, how perfectly rammed earth or an earth facade helps here to modulate and to average the moisture. You see in the gray bar on the top some top wings coming out. That was when the client was not aware at what time of a year he has to close the windows and stuff like that. So it's always the same issue. If you build a sustainable, less technical orientated building, it needs to be very well educated with the client, that the client performs and acts with the house in a proper way. So that is the building. Most likely Martin will tell you a bit more. Thank you very much for your attention. I hope it was okay. Thank you.
Thank you so much, Martin. Very, very good. We are on time. Da switcher jeg til norsk. Da går vi fra tyske arkitekt Martin Haas til østerrikske Martin Rauch, som nå i 37 år har vært dypt involvert i jordbyggingsprosjekter på internasjonalt nivå. Siden 2003 har Martin Rauch blant annet undervist ved University for Art and Industrial Design Linz og ETH Zürich. I 2010 ble Martin Rauch UNESCOs æresprofessor i jordarkitektur, bygningskulturer og bærekraftig utvikling. Vi har bedt Martin presentere hans nye prefabrikerte stampejordelementfabrikk, og Martin med oss I dag. Are you with us?
Yeah, Martin has shown a lot of the picture from the prefabrication, so I share very few picture from the production in Darmstadt in the factory. But what I want to start, what is earth, clay? What is the material with we can build this rammed earth blocks? It is mostly material from all over the world, and earth construction or clay for building this earth is the result of erosion everywhere in the world. From the mountain, if the particles get always smaller and smaller, then you have the glue, then you can see that's the glue. And on this eroded material, the wood is growing, the plant is growing, there is the life, earth and water and sun. And this is the building material what we use, and I think it is the building material for the future, and mostly it is the excavation of our buildings, because the excavation of the buildings will get always bigger and bigger, and there is a more amount, and it is really a problem, the excavation material. We have to learn that the excavation material of the building is our researches. And if we take the excavation and we prepare it, we can build the house, and if it goes back to the ground or to the nature, so the circle is very small and healthy. And the idea is 100% earth, only with no adding of cement or chemical situation. Only take the earth in the right quality, fill it in a formwork, ramming, then you can make prefabricated element, what Martin has shown you in the last pictures. You set this on the foundation, lift it there, and it is very helpful that the joint of this prefabricated element, you can retouch it, that you don't see the joints anymore. And the sense of this material is compact earth together with stones. The clay is the glue between, like cement. It is nearly like cement building construction, but not with cement. It is only the clay who holds together the components, and if it is dry, so it is hard, strong enough, and if you add water again, so you can reuse it 100% with no quality losing. So earth construction is really a perfect recycling material. You can use it every time again with no losing the quality. I have long experience in earth construction, about over 35 years, and I'm always look for two calculated words. It is the calculated risk. The calculated risk, I want to make some buildings where I'm always learn if I lean out a little bit of the window, but not so much that the project is losing. So, but it is very important for the innovation, because if we make no calculated risk, we have no innovation. And the second part is the calculated erosion. And here you see the image from the inside, the rough earth, 100% earth with no cement, with no chemical, is only dry, rammed earth construction. and also how you can use this also in winter, in raining areas with very less roof. It is the calculated erosion. The calculated erosion means that it's like the nature, that the water is running down over the wall. The small pieces of clay wash out, and the stone and the conglomerate of the stones are holding the erosion back. And maybe bricks like here, or some plaster lines like by Natura, they stop the deep erosion. The calculated erosion, it is not a technical problem, it is more a psychological problem, because some clients are afraid if the water run over this wall down, and the surface get more rough. Here you can see the Regular Kräuterzentrum in Laufen. We have built it together with Herzog de Marot. It is a factory 110 meter long, as 30 meter wide, 12 meter high, and it is built with 607 prefabricated elements, like a wall around the construction. And normally we build with concrete. The concrete is a wonderful material, but the problem is that we use it too much, too inflationary. So we have to change. And I think the future possibility is that we can use earth and wood construction together with earth elements. We can produce earth element in a very high technical performance, and it could be much more in future. And we would build big blocks and ceiling with wood like this. These are the images what you have seen before. We can not to change the material. We have to develop the machinery, the tools. We have to develop new tools to make earth construction for a future working. So it's what you have seen before. It is really a very interesting project because it is 12 meter high blocks. You can walls. You can really build huge towns with this material if you would like. So it is possible to change. And in the moment I'm planning and building my own prefabricated elements. It is a manufacture of research work and to build earth construction with the machinery. This is the Thos wall. It is 12 meter high walls to the living space. It is like very rammed earth, acoustic wall that no noise can go through the wall, and it is a combination between solar energy for heating to dry the elements, and inside the earth's walls are load buried. I think it is possible to build really big buildings in load buried earth construction, like our production hall here in the building state. Here you see also on the left side the machinery what we have used in Darmstadt in Al Natura project. We have developed this machinery, and this machinery is always we add always some new tools to change. And we make also, there you see that is a 40 meter long wall. You can ramming and then prefabricated the elements. And you see that also the structure of the wood is load buried on the 67-meter long wall and 8-meter high. We make also in the moment very much research work because it is very important to get the quality of the earth's numbers and norms and results. And actually, yesterday we started to make really 3-meter high wall pressure to develop that we can build load-buried earth houses together with wood construction. And here is one prototype. You see the big block you lay on the layer of layer with clay plaster together, and in the meantime we make details catalog how we can join earth construction, isolation, inside isolation, outside isolation. It is really growing, and that the important that we get less concrete, more earth, more wood. It is, I think, it is time to reduce the climate, also the CO2 production of this cement like this to find a right way. And so the future for me is earth block wood, so we can really build towns. And at last build I want to show there is also 2 books what I will show you. It is about the Erde, konstruieren mit Stampflehm und upscaling earth. So thank you very much, and I hope I'm in time.
You are on time. Thank you so much, Martin. Da tenkte vi det ble tid for et norskt innslag med Bjørn Kierulf. Opprinnelig utdannet i industriell design og fra 2007 internasjonal kjent passivhusspesialist. Men ettersom Bjørn har vært bosatt i Slovakia siden 1989, hvor han siden 2011 har vært involvert i EcoCocon, et internasjonalt firma han nå er CEO for, blir også denne presentasjonen på engelsk og presentert forhåndsinnspilt. Men igjen, still gjerne spørsmål, de blir besvart og sendt ut i etterkant. Vær så god, Bjørn.
Hi, I'm Bjørn Kierulf, the CEO of EcoCocon. I'm here in my office, a load-bearing straw bale dough. Today I'm going to present you a little bit more mainstream way of building with straw, the EcoCocon panels.
It can be said that the wall system is really designed by nature. We use very little wood and a lot of infill straw, and in combination we create a modular load-bearing system. We started more than 10 years ago. The panels and the ideas for the panels originated in Lithuania. We now have the headquarters in Slovakia and a network of partners all over Europe. Our goal is in the future to have production sites in the various regions of Europe so that the transport distances will be as short as possible. Now, why straw? First of all, it's a natural carbon sink, it's rapidly renewable, and it's abundant. By using more straw and less wood, we in fact have a more sustainable solution. Straw insulates much better than wood, and as you might be surprised, it doesn't burn very well. In fact, straw has a high content of silica, a natural fire retardant, so there are no additives that need to be added to the straw to provide fire protection. A future-proof construction system is based not only on carbon storing materials, but should also be a Passive House certified component. Then saving energy means having a very efficient envelope. We also, because of our diffusion open way of building, are able to create the optimal humidity and the very high indoor comfort. Due to its modularity, we can adapt to any design and provide very quick installation of the panels as such. The wall build-up is very simple. We have a load-bearing element that is filled with straw. That is the main core of the construction system. On the inside surface, we can apply clay plaster directly onto the straw. We can also, of course, use other materials like gypsum boards and so on, but the ability to add wet clay plaster directly on the straw is unique. On the outside, we use airtight diffusion open membrane and a wood fiber board to add some extra insulation and protect the panel against wind and rain. The technical characteristics are quite impressive. We have achieved with 25 mm clay plaster a fire resistance of array 120, and with a wood fiber board without any further plaster, array 120 EF. Our panels can take a standard load of 35 kilonewton per meter, but also peak loads of up to 110 kilonewton per meter, and all that with a new value of 0.12. And not to forget, we can sequester through the materials nearly 100 kilogram of CO2 per square meter. And of course, it's a certified building block. We have certified it as a cradle-to-cradle product. It also is a certified passive house element. And as I mentioned before, we have very good fire ratings, which we achieved in our tests. Circular design for minimal impact is very important. We therefore think that the cradle-to-cradle certification is a very important part of our system. Also because we use nearly no glue in our construction, and we can achieve a very high material health and also a very low amount of CO2 emitted in the production, which is very often overseen. So if we compare it, for example, with CLT panels, our panels have a much lower amount and much lower need for energy in production. The whole system is Lego-like. That means that our engineer takes your design, then transforms it into these modular blocks using one of our 6 types of panels, and we get more or less a numbered building set, which then can be easily assembled on the building site. Please note that also reinforcements for lateral forces and so on, or even lintels, are being included in the design, and are also all filled with straw, of course. So we think that our way of building is not only tackling climate change, but providing a healthy and high comfort indoor climate at the same time. We can have one study here, a gym in Holland. The size was 746 square meters, and we were able to sequester 50 tons of CO2 through the use of our panels. In fact, the Venlo municipality chose our wall system because it had to use cradle-to-cradle certified materials. And these materials are, in fact, not many on the market yet. So the goal was to contribute to a healthy, pleasant, and sustainable living environment. So it's really about becoming a sustainability pioneer. Through our or with our panels, you are able to design houses that are sustainable, that can have all the positive elements you're looking for as an architect, but also as a developer who is looking for higher quality at comparable costs and the use of efficient pre-assembly. We think that we have found a solution that enables us to build all kinds of buildings, and we hope that you can follow us in our footsteps, and looking forward to cooperation, future cooperation. Thank you very much for your attention.
Tusen takk, Bjørn. Veldig spennende. Da har vi lært mye om hvordan vi kan bygge vegger i lavkarbonmaterialer, og vi ser også at en del av spørsmålene blir besvart under presentasjonene, og også vil bli besvart på neste foredrag, og også Max sitt senere. Nå reiser vi tilbake til Tyskland for den neste presentasjonen fra daglig leder av Hvem. Han heter Hagen Ellert. Hvem et firma som lenge har produsert leirpuss og leirpaneler som alternativ til gipsplater, og nå har utviklet klimapaneler. En mulighet for effektiv kjøling og oppvarming av både eksisterende og nybygg. Da sier vi vær så god til Hagen Ellert, Managing Director of Hvem. Vær så god.
We have been developing and producing heating and cooling systems since 1999. Our systems are based on natural materials, especially clay and wood. Our main product is our Klima panel. It's a 25 millimeter thick clay panel with pipes or electric cables inside. These panels are 62.5 centimeters wide, and we have three sizes from a height of 80 centimeters, 1 meter 60, and 2 meters. The panels are made of prepared clay. We mix clay with only the special kinds of sand and plant fibers. In the surfaces, we add a glass mesh on both sides. We have special panels for cooling and the ceilings. In this panels we add a little bit of dispersion, but it's less than 1%. We do it to make it not waterproof, but to stabilize it a little bit for the case it's getting wet or moisty. If you cool too much, then it can condensate at the panels and it can get wet. In addition, for our climate panels, we offer normal clay panels without cables or pipes. We also have clay plasters and clay colors. We produce all the things here in Focus. Also, we offer hydraulical and electrical things to complete our systems. And we add our customers with planning and calculation for the projects. Most of our projects are private houses and hotels, wooden houses, and monuments. We have a lot of monuments as customers. We combine clay and pellet heating, besides the environmental effects, to get a perfect indoor climate. This is determined by following aspects. Temperature. Humans usually feel comfortable at temperatures around 20 to 25 degrees. That is why we heat and cool. But also the temperature distribution is important. And this is very balanced with panel heating. Heated surfaces radiate onto unheated surfaces and warm them up as well. So after a while, there's an even temperature distribution throughout the room. Air circulation. Conventional heating systems heat the air through convection, means by air circulation. Not so with panel heating systems. Panel heatings radiate. Surface cooling also works with heat radiation. Only in reverse. The human body radiates to the cool surfaces. Humidity. Comfortable humidity is around about 40 to 50%, and clay is able to absorb a lot of moisture and to release it when the air becomes too dry. This makes it possible to keep the humidity within certain limits. Acoustics. Clay is a heavy and soft material and has good properties of sound absorption. Also because it's rough, mostly rough surface. We do not use chemical additives that produce emissions or odor. So we also have good air quality with clay in the room. Now to the environmental aspects. For heating with panels, we only need low water temperatures, around 30 to 40 degrees. So it's suitable to heat for heating pumps or gas condensing heaters. The lower the water temperature, the more efficient these devices are, and we get better carbon dioxide footprint. You see in the chart, a conventional heater produces about twice as much carbon like a heating pump. Now we have normal oil or gas heaters. We have around about 320 grams per kilowatt hour carbon. In opposite of gas heating pumps, we have 150 to 200 grams per kilowatt hour. And if you combine the heating pump with renewable energies, we can reduce the carbon content even further. In opposite to other systems, we save a lot of energy and also carbon dioxide on the manufacturing and selection of the materials. More than 2 megajoules of energy are needed to produce cement or gypsum. Clay mined from clay pits also requires more than 1 megajoule. The clay we use is a waste product from mining ceramic clay or from construction sites from excavation. To get ready material, we don't need any terminal process. We only have to crush it and mix it with sand and plant fibers. Most of the energy we need is for drying the shade panels, and for this we use combined heat power station. gas motor to produce electrical energies and heat as well. And we use a heat recovery with heating pump. The rest of the heat, with a very low temperature, which we can no longer use for drying, use for heating our building. That's possible only with heating panels. This is our company building, 2,000 square meter production and warehouse, and around about 300 square meters of office on 2 floors. We built it in 2018, and of course we use all our systems for the building. The warehouse and production is heated by a floor heating system in the concrete floor, and the office is heated and cooled by climate panels in the ceiling. You can see it here. For mounting, we need a panel lifter, and the panels are screwed on a metal construction, a standard metal construction. The washers to screw the panels are already mounted in the panels. Our office has 333 square meters, the heating load from 14 kilowatt, cooling load from 9.7 kilowatt. We use 35 to 30 degree water temperature for heating and 18-16 for cooling. It's not possible with the system to cool down the office to 20 degrees when it's outside temperature from 40 degrees. But last summer it was really hot here in Koblenz. We had 35 to 38 degree outside temperature, and in the office not more than 25 degrees. It was comfortable and a good climate to work. The panels are connected with pipe ends, prefabricated pipe ends in the cavity of the ceiling. We connect maximum of 5 panels for one heating circuit. And heating circuits are connected with manifolds. The manifolds also mounted in the ceiling cavity. The remaining surfaces are closed with clay panels without pipes. With plates without pipes, we can be cut to the right side. The last step is plastering the ceiling with 2 layers of clay plasters. Each layer is around about 3 to 4 millimeters, and in between the layers is a glass mesh. This is our office now, ground floor and first floor. The interior walls are wood frames covered with clay panels as well. Clay panels without pipes. The exterior walls, stone walls, are covered also with clay. The floor is constructed with wood fiber panels and wooden floorboards or boards in the first floor and linoleum in the ground floor. All in all, it's a nearly perfect climate here in office. On our website, we have presented some facilities where you can experience the climate for yourself. Mostly hotels, restaurants, museums. Most of them are in Germany and in other countries of Central Europe. Some overseas, but unfortunately none in Norway or in other northern European countries. So, all in all, in summary, I think that our climate elements are suitable for reducing carbon dioxide emissions. Firstly, we use secondary rough material, clay that is produced anyway on building pits or mining clay for ceramics. Instead of deposing it, we process it further. And the second thing is the water temperature. We only use low water temperature during heating. So we can use efficient low temperature heaters like heating pumps. So, thank you for your attention.
Tusen takk, Hagen Ellert. Bra. Da er vi på siste foredrag, en 10 minutters innlegg. Og sist men ikke minst er dette fra Tekna medlem, og som også er medlem av bygg og anlegg. Danske sivilingeniør i miljø og plan, Max Wittrup Jensen. Han er bosatt på Hurum etter mange år som internasjonal pioner innen bygg og halm og leire i Sentral-Europa. Etter 8 år som selvstendig miljøkonsulent er Max nå i ferd med å oppstarte LavKarbonBygg AS for å bistå med å akselerere introduksjonen av materialer som dem vi har fått presentert i dag i Norge. Max har kommet med oss i dag for å vise spennvidden av den kommersielle utviklingen innen feltet de siste 20 år rundt om i verden. Og det var Max som var initiativtaker i dag, og han er faktisk med oss i studio, så det er ekstra hyggelig. Da skal du få lov til å introdusere deg selv, Max, og så går jeg ut. Vær så god.
Hej. Tusind tak for chancen for at være her. Der kom jeg med på skærmen, greit. Jeg har nu boet her i over 8 år, og jeg kender mig lidt som den lille gut i Kejserens nye klær, når jeg har set den norske byggeteknik, moderne byggeteknik, på grund af min baggrund inden for dette felt, som jeg nu har set. Så derfor så har jeg inviteret jer med på denne rejse, der jeg har lyttet til eksperterne. Nu bliver det stort set eye candy, som jeg viser her. Hvordan det her det er vanligt. Så det er ikke noget, man trænger pilotprojekter til i Norge, Innovations Norge og så videre. Det er bare at ringe, e-mail, så fikser vi det. Vær så god. Lad os starte rejsen med dette halmhus, som er bra og sundt til trods for sin modne alder. Det er netop blevet erklæret et nationalmonument. Men herhjemme, bare 600 meter fra Skaugum-gård, ligger dette diskrete stampejordhus fra 1972-73, nu isoleret med klædning. Men stampejord kan jo så mye mere. Her fra en dyrepark. Det kan ofte erstatte beton, så længe væggene har tørre fødder. Jord har naturligt mange farver, som kan blandes, eller vi kan gå for det mere rustikke look. Her til lands trænger vi overhæng, men helst af massiv træ der. Men dette bygget i Schweiz får lige mye snø som i Norge. Instinktivt tænker vi, stampejordsvægge må holdes tørre, men det er en sandhed med modifikationer. Jord kan være urbant og trendy, eller sikre et bra og lydsvagt arbejdsmiljø. Massive stampejordsvægge er bra til mange ting, men typisk ikke til at isolere. Så nu til noget andet. Hempcrete er et relativt nyt koncept, hvor biter af hamphalmen bliver blandet med kalk. Derved opnås et stærkt, relativt let og isolerende materiale, som kan bygges med på samme vis som stampelejre, som i dette atelier i Tjekkiet. Eller hvad med et varehus? Her set ydefra, og det stod færdigt i 2019. Vanskeligt ikke at tænke Nederland, når man nævner hamp, så her er et stort boligprojekt fra Nederland med præfabrikeret hempcrete. Men halm er også vældig velegnet til isolering, eller alle typer matter. Her fra en stor dansk hampavler, der har specialiseret sig i at omdanne naturfiber, genbrugsfiber, blandt andet til biler, møbler, men ikke mindst isolation. Hampisolering kommer i mange cykluser og er mye behageligere at jobbe med end mineralisolering. Nu til halmbyg. Det er fuldt muligt at bygge med store halmballer, som her, hvor arkitekt Werner Schmidt stod for konstruktionen af dette passivhus økohotel. Jumboballerne kan også dækkes med klædning, som her i Italia. I England bliver sociale boliger iblandt bygget af halmballer og pysset udvendigt med kalkpys, Her er det de små halmballer. Eller hele skoler bliver bygget af halmballer i trækonstruktion, ligeledes med traditionel kalkpys udvendigt. På denne engelske skole af halm blev de mest eksponerede vægge dækket med klædning, akkurat som dette skoletilbyg i Berlin. Halm kan anvendes til efterisolering af gamle boligblokke, som her i Frankrike, eller i Tyskland, hvor specielle plastanker blev udviklet til formålet for at forhindre kyldebrud. Ved et byg i Frankrike blev en live brandtest udført. Noget som igen viste, at velpakket halm er mere brandsikker end de fleste byggematerialer. Men lad os se nærmere på byggeprocessen og brandtest. Jeg anbefaler præfab halmbyg til Norge. Byggeballer er helst ekstra bra komprimeret. Dette er en mobil byggeballepres. Rammer bliver fabrikeret på forskellig vis af omlag 7-10 forskellige fabrikanter. Vægelementerne er enkle at transportere. Nogle producerer hele vægge, som her i Tyskland. Eller Isopal i Frankrike. Men ikke glemt, at også gulve kan lages af præfab. Panelerne løftes på plads, placeres, samles. Dette projekt er for stort for halm. For tiden bygges dette i Tyskland. Dette er en typisk lejresprøjte, den sikrer bra hæftelse med halmen. I Frankrike bygger de en 0 energi, 0 carbonudslip skole. Sådan kan det gøres. I Oslo har vi Christian Augustgade 13, anno 2021. Her Amsterdam anno 2009. Det tog en uge at stakke yttervægger, tak og lukke det 5-etages byg. Disse dage er det travlt ved et kloster i Tyskland. Her bygges nemlig Tysklands største halmhus. Af klosterets egen halm og tømmer. I England bygger de præfab søjler af halm dyrket 100 meter fra bygget. Og i Nederland blev denne sportshal isoleret med indsprøjtet halmfiber. Dirk Scharmer i Tyskland holder på med lejlighedsbyg og præfab halm med kalkpys. Mens Werner Schmidt i Schweiz tager det et skridt videre og bygger hele halmmodulbyg. Halm gemmer sig nogle gange bag klædning, andre gange bag myrsten. Hvem skulle tro dette byg er af halm? Eller denne skole? Og hvad med denne barnehage? Lidt inspiration til lejerpys i moderne byg. Og ikke glem præfab lejerpaneler, også til køl eller varme. Der er jeg næsten færdig. Her nogle byg er kompresserede, ubrændte lejersten. eller hvad med en facade af kork? Naturen byder på mange muligheder. Her er et offentligt byg med strå. Inden jeg afslutter, har jeg et lille spørgsmål til dere, som har barn. Hvordan tror dere, akustikken er i dette rum i forhold til et med lejerpys? Hej, der bliver det live igen. Jeg afsluttede med det sidste billede for at vise, at klimakrisen krasser. Vi har ikke tid at vente på lange løsninger. LavKarbonBygg er bra, massiv træ er bra, men om vi kan få mere af disse metoder ind, der klarer vi det mye bedre. Det var alt fra mig. Tak.
Tusen takk, Max, for en spennende presentasjon, og tusen takk for at du tok initiativet til denne sendingen. Da ble jeg justert. Tusen takk til alle dere som så på, tusen takk til forelesere, og så minner vi om at spørsmålene deres som ikke har blitt besvart, blir besvart og sendt ut i mail til alle dere som har meldt dere på. Og se gjerne på Tekna Klima, Tekna Bygg og Anlegg og Tekna Biomangfold for fremtidige arrangementer, og så ses vi snart igjen. Ha det bra!